In part 4 of this series, we're going to discuss factoring by grouping. This is a method you can use when you have a fairly lengthy polynomial that doesn't have an obvious greatest common factor among all of the terms. Check out the following example. 2y to the third power plus 14y to the second power plus 10y plus 70. When we look at this polynomial, we can see that there is actually a greatest common factor among all of the terms here. But you'll see as we move through the example that there's actually more factoring in addition to that we can also do. But we'll start with that greatest common factor. So what do you see here among these 4 terms that is a common factor? You might want to pause the video here to give this some thought yourself. The greatest common factor here is the number 2. So let's start by factoring out that 2. 2 goes on the outside, we open up a set of parentheses here. 2y to the third power divided by 2 leaves us with y to the third power. We're also left with a 7y squared and a 5y and a 35. So we have successfully factored out this constant, this number 2, but there's still all of this stuff here. There's this whole polynomial in parentheses, and in fact, we can factor this even further. To do this, we will factor this interior polynomial using the process of factoring by grouping. So to start this process, I like to just distinguish the 2 groups that I want to factor separately. Now there are many ways to do this. You can rewrite this with spaces in between. I do have a little highlighter feature here, so I'm just going to highlight my first group, and I'm going to highlight my second group in a different color. And we're going to factor each of these groups separately. So the group on the left-hand side, that's the group highlighted in pink, we'll start with just those 2 terms. What is the greatest common factor among those 2 terms? Again, you might want to pause to think about it yourself. The greatest common factor here is a y squared. We don't have a number directly on this y cubed term here. This 2 doesn't count, he's already factored out. So we can't consider any numbers as part of this greatest common factor. We will just use the letter y. And our greatest common factor for y is this y squared that divides evenly into itself and y cubed. So when we factor out the y squared, our polynomial will look like this. We still have the 2 on the outside. And in this group here on the inside, we have also found that y squared is a common factor, and we can factor that out, and we are left with a y plus 7 for our first group. We can do the same thing with the group in blue, 5y plus 35. What is the greatest common factor among those 2 terms? In this case, it's that number 5. 5 divides evenly into 5y and also 35. We can't include any y's in our common factor because there is no y in this 35 constant term. So when we factor out that number 5, here's what it will look like. We will have still our plus sign here, the number 5, and then we'll do our factoring here. So 5y divided by 5 leaves us with a y, and 35 divided by 5 will leave us with the number 7. When we think of this process in small pieces like this, it becomes much less intimidating. We're just factoring smaller polynomials, and then we're working with this whole big polynomial together in the final steps. Once we've factored each of our groups, which we've done here in the pink and in the blue, what we can now do is consider the entire polynomial once again that we have inside this large set of parentheses. And we want to look at this in terms of factoring out a binomial. So we talked about how sometimes a binomial can be a common factor in the previous parts of this series. So do you see here among these two big terms anything that's similar that they have in common? If you notice that they both have a y plus 7, then you are exactly right. That y plus 7 itself is our common factor among those two terms. So let's factor out that binomial within our large polynomial. The 2 will stay on the outside. Our new factor that we're factoring out here is this y plus 7. So I'm going to write that down next. Y plus 7. And then we're going to divide each of these terms by that y plus 7 and write down what's left here in parentheses. So let's clean that up a little bit first. We're going to first divide this first term by y plus 7. And when we do that, we're left with just the y squared. So a y squared will go here. And then in the second term, we're going to divide that by our y plus 7. And when we do that, we're left with just this 5. So our 5 will go here. What you can see here is that first of all, we have parentheses all over the place, and some of them are not really necessary. At this point, we have three things multiplied by each other. We have a 2 times a y plus 7 times a y squared plus 5. And since this is all multiplication, we can do it in any order, and the outcome will not be any different. That means that we can eliminate some of these parentheses. In fact, we can eliminate these big parentheses here at this point without changing the meaning of what we have. So we can write this as 2 times y plus 7 times y squared plus 5. Now check this out. This is very cool. We have here three factors. The factor of 2 multiplied by the factor of y plus 7 multiplied by the factor of y squared plus 5. Three factors multiplied together that create our original polynomial. Since each of these factors do not contain common factors within them, we can't factor them any further. This means that we have completely factored our original polynomial successfully. So this would be your solution in a problem where you were asked to factor this polynomial by grouping. Pretty neat, huh? Let's try another one together. How about this example? 10x squared plus 5x plus 4x plus 2. Now, in this example, unlike the previous one, it looks like there isn't exactly a common factor among all four terms. I can tell by first looking at the numbers, 10, 5, 4, and 2. There's no common factor among all of those. It's primarily that 5, the odd number, that throws that off. Among the letters here, we have an x in only the first three terms, but not in the fourth term. So I can't use an x as part of a greatest common factor either. This means that there is no greatest common factor among all four terms other than the number 1. But that doesn't mean that we cannot factor this polynomial. We can use the process of factoring by grouping like we did in the previous example. Lucky us, we get to skip that first step of factoring out a greatest common factor because there isn't one, and we get to jump right into factoring each of our groups. So I'm going to start by identifying each of the groups here, our pink group and our blue group. So let's focus on the pink one first. What is the greatest common factor between 10x squared and 5x? You might want to pause to think about it. In this case, that common factor is 5x. We can pull out a 5x. Then we will see what's left when we create an equivalent expression. So 10x squared divided by 5x, that's the operation that we want to do first. That will leave us with a 2x. And then we will take 5x divided by 5x. Anything divided by itself, remember, equals 1. All right, in our second group here, 4x plus 2. What is the common factor between those two terms? That common factor is the number 2. So I'll write down my 2, and then I'll divide 4x by 2. That will give me a 2x. Then I'll divide 2 by 2. Anything divided by itself, once again, is the number 1. Now lucky us, just like in the previous problem, you might notice that we have something repeating here. We have a 2x plus 1 on the left and a 2x plus 1 on the right. And that means we're headed in the right direction. That means that this will successfully factor by grouping. Sometimes it helps to have this insight when you start the problem. It can help you factor this second group because it shows you what binomial you're aiming to find in that second group. So sometimes having a little bit of a vision of where you're going can help you along the way. From here, we're going to go back to considering this polynomial as a whole. What we have here are two terms. They're big, crazy looking terms, but there's just two of them added together. And we want to find common factors among these two terms. So we'll look for anything that is similar. Remember, a common factor can be a binomial. So in this case, what's in common is the 2x plus 1. It's in both places. So we can factor out that 2x plus 1 the way we factored out any other factor. So that will look like this. We'll pull it out on the left, 2x plus 1, and then we'll divide the left term by 2x plus 1, and the 2x plus 1s will go away. We'll be left with a 5x, and then we'll divide the right-hand term by 2x plus 1, leaving us with just this 2. What we have here is 2x plus 1 times 5x plus 2. These are two factors, and when multiplied together, they create our original polynomial, which is pretty neat. We can check our work by looking at each of these factors individually and making sure that there are no other common factors in them. In this case, there aren't. So it looks like we are done with our work of factoring this polynomial by grouping. Now, it's worth noting that not every polynomial is factorable, and we run into this sometimes when we're trying to factor something by grouping and it just doesn't work. This is often an indication that we have a polynomial that is just not factorable. Let's have a look at this example, and we'll try to factor it. M to the third power plus 3m squared plus 13m minus 15. We'll try to factor this in a similar way to the previous problems. There is no common factor among all four terms, so we'll skip ahead right to grouping. Our first group, m to the third power plus 3m squared, and our second group will be 13m minus 15. Now the first group can be factored. M to the third power plus 3m squared, that has a common factor of m squared. And when we factor out the m squared, we're left with m plus 3. Now let's look at the second group, 13m minus 15. Now the ultimate goal here is to get this to look a little bit like our first group. In particular, we want to have the same binomial so that we can factor it out. So we're hoping that we end up with this binomial here, m plus 3, and we're hoping that there is some common factor that will factor out to give us that m plus 3. Now let's see if that's even possible. To get m plus 3 here, well, our negative 15, that 3 would have to be multiplied by a negative 5. So we would need a negative 5 in this spot here. Negative 5 times 3 gives us negative 15. That's good. But negative 5 times m is never going to give us a 13m. It's just impossible. And there is no other way that we can get this negative 15 from a positive 3. There's also no other way that we could have factored our first group. All of these things indicate for us that this polynomial is not factorable. So not going to happen here in the second group. When we run into this situation, the solution to your problem will just be not factorable. And that's okay. Not every polynomial can be factored by grouping or can be factored further at all. Let's try the following practice problems. Here we have 4 polynomials that might be able to be factored by grouping. If you can factor them by grouping, please do so and leave the factored form in the comments below. You can compare your work to your classmates to correct each other and to check your own work. If something is not factorable, then state that it is not factorable. You might also want to include a little explanation of how you know that this polynomial is not factorable.